Have you ever wondered what holds everything together? Look at your hand, the desk, the air you breathe. It's all made of tiny, tiny things called atoms. Billions and billions of them. But what keeps those atoms from just falling apart into dust? The answer is a little particle that gets almost no attention, but it is one of the most important players in the universe. It's called a neutron. It's the silent partner, the unseen glue, the quiet hero inside every single atom that makes up our world. It's time we gave this amazing particle the spotlight it truly deserves. Without neutrons, the world as we know it simply couldn't exist. Think about that for a second. The very chair you are sitting on relies on these subatomic, smaller than an atom particles to stay solid. They are so small you could never see one, not even with the most powerful microscope in the world. Yet they are working hard constantly, performing a crucial job that allows for the amazing variety of substances we see around us. The water in our oceans, the iron in our blood. They are the unsung heroes of the atomic world. And understanding them helps us understand everything. So why do these neutrons matter so much? Their job is all about balance and stability. To understand the neutron, we first need to zoom way, way in on an atom. An atom is like a miniature solar system. At the very center is a dense core called the nucleus. This is where the action happens. The nucleus is made up of two types of particles squished together: protons, neutrons. Protons are the positive thinkers of the atom. They have a positive electrical charge. Orbiting far, far away from this nucleus are the electrons, which are tiny particles with a negative charge. It's the attraction between the positive protons and the negative electrons that keeps the electrons from flying away. Now, let's focus on our star player, the neutron. The neutron is the proton's roommate in the nucleus, but it has a very different personality. It has no electrical charge at all. It's neutral, which is where it gets its name. This lack of charge is incredibly important. It means neutrons don't get involved in the electrical pushing and pulling that protons and electrons do. They are the calm, cool, and collected residents of the atom. They just hang out in the nucleus, adding weight, and keeping the peace between all the other rowdy particles that are buzzing around them. One of the neutron's main jobs is to give an atom its mass. Mass is just a scientific word for how much stuff is in an object. Electrons are super lightweight. Protons are heavy. Neutrons are heavy. They are much, much more massive. In fact, a neutron has just slightly more mass than a proton. This means that almost all of an atom's weight comes from its nucleus. Here's a puzzle. Protons all have a positive charge. Like charges repel, think magnets. Two positive ends of magnets push apart. Same rule applies to protons. If you cram many protons into a tiny nucleus, they should push each other away with huge force. The nucleus should explode in a shower of particles. So why doesn't it? The answer is the neutron, the atomic peacemaker. Neutrons act like special glue. They activate the strong nuclear force. The strong force is the strongest force known, but it only works across nuclear distances, very short. It's like super sticky tape that only works when things touch. The strong force pulls protons together. It also pulls neutrons together. It's far stronger than electrical repulsion. Neutrons add stickiness without adding repulsive charge. Imagine rowdy friends who all want attention, our protons. Put them in a small room and they'll shove each other. Now bring in calm, quiet friends, our neutrons. They don't shove, they stand between the rowdy friends. Their presence prevents fights and provides a buffer. That's exactly what neutrons do in the nucleus. Without enough neutrons, a nucleus becomes unstable. Too many protons without enough neutrons. Repulsive force wins. The nucleus can break apart. This is radioactive decay. It releases energy. Some atoms are radioactive because their nuclei aren't stable. They don't have the right proton to neutron balance. Neutrons are critical stabilizers for most elements, especially heavy elements that need lots of glue to hold protons together. Neutrons do another cool thing. They create different versions of the same element. The identity of an element is determined only by the number of protons it has. Any atom with 1 proton is always a hydrogen atom. Any atom with 6 protons is always a carbon atom. That number is like the atom's unchangeable social security number. But the number of neutrons can change. Carbon with 6 neutrons. Carbon with 7 neutrons. Carbon with 8 neutrons. It's still carbon, just a different flavor. Those different versions are called isotopes. Isotopes, same protons, different neutrons. Example, carbon. Carbon-12 is the most common isotope. 12 equals protons, 6 plus neutrons, 6. Carbon-14 is another famous one. Carbon-14, 6 protons, plus 8 neutrons, thus 14. That extra weight and different neutron-to-proton ratio makes carbon-14 unstable, radioactive. Real-world example, archaeology and paleontology. Living things, plants and animals, take in carbon while they're alive. A tiny predictable fraction of that carbon is carbon-14. When the organism dies, it stops taking in carbon. The carbon-14 begins to decay at a steady, known rate. By measuring how much carbon-14 remains, scientists can calculate how long ago it died. Isotopes are useful across many fields. Medicine. Radioactive isotopes targeted to specific body parts. Track their radiation to image organs and find tumors. Smoke detectors use specific isotopes. Food preservation uses isotopes. Scientific research uses isotopes. All because atoms can have a few more or fewer of those neutral particles, neutrons, in their core. What a difference a neutron makes. These little particles are central to nuclear energy. In a nuclear power plant, scientists use neutrons like tiny billiard balls. One neutron is shot at a large, unstable nucleus, like uranium-235. The neutron hits, the giant nucleus splits into smaller pieces. This splitting is nuclear fission, releasing huge energy, mostly heat. The split uranium nucleus also releases 2 or 3 new neutrons. Those neutrons fly off and strike other uranium nuclei. Each split makes more energy and more neutrons, cascading. This cascading is a chain reaction. Nuclear plants control the chain reaction carefully. They use the heat to boil water, create steam, turn turbines, generate electricity for our homes and cities. Uncontrolled, the same principle powers nuclear weapons. An uncontrolled chain reaction releases massive energy at once. It shows how much power is locked inside the nucleus, held in check by neutrons. From clean energy to destruction, neutrons are at the heart of the nuclear age. So what's the big takeaway? Neutrons seem quiet and boring, no charge. They don't push or pull, but they are absolutely essential. Without them, protons would fly apart. Only the simplest atoms could exist. No carbon for life, no oxygen to breathe, no iron for our buildings. These neutral particles provide the mass that gives matter substance. They are the nuclear glue that holds it together. Calm, strong, silent. Without them, the universe would fall apart. Remember that the next time you think about what makes the world work. By the end, you'll see why the neutron, this particle with no charge, is actually a superstar of science. Let's get started on our atomic adventure, shall we?